For Tuesday, regular exam group. You know the operating procedure. For those of you who've indicated a need to do the exam earlier in the day, I've managed to secure a small conference room right over here. Over here in Pugh Hall, which is pretty close by. If you don't know where it is and you need to go there, find out where it is. It's not hard to find. It's on the first floor. Just walk in and wiggle around the halls a little bit, you'll find it. Noon to 6 p.m. So, I'll now take a look at the notes you presented me. And based on the time slot you would prefer, try to accommodate you accordingly. If any of you still need to submit a note, do it. Now, last part of chapter 22, electrochemical arithmetic, for which there are two general aspects: Faraday's law and the Nernst equation. In the main, Faraday's law applies to the operation of a voltaic cell in reverse, recharging the cell, running a current through the cell rather than using the cell to give us a current. Running a current through the cell to regenerate original cell components. You got a device in your car which operates on the principle of Faraday's law? You got a generator? Got an alternator? Then you're operating on the principle of Faraday's law. Because what that device does is, after you've got the car started and you're motoring down the road, the alternator or generator recharges the battery by running the battery in reverse. Arithmetically, calculations involving Faraday's law really rest on dimensional analysis. Call it unit analysis if you prefer. Pay attention to units. The algebraic form of Faraday's law is this. Those are the quantities. This is mass of material. For example, if you electrolyze a molten metal chloride, you can calculate mass of metal produced at the cathode, the electrode at which reduction occurs, or, if it's a metal chloride, mass of chlorine produced at the anode, because that anode is the electrode at which oxidation occurs. Now, this Q symbol, unfortunately, is used in a lot of ways in chemistry. In this case, Q means charge in coulombs. This squiggle is formula mass. F is the Faraday. Here, Faraday is just a unit of electrical charge named in honor of Michael Faraday. It's the total electrical charge borne by a mole of electrons. Now, an individual electron doesn't have much charge. But when you got an Avogadro's number of electrons, you wind up with 96,500 coulombs. And the coulomb unit-wise is equivalent to an amp current times second, the time during which the current flows. Multiply current times time, you get total charge transferred in coulombs. N is moles of electricity transferred. You can only determine N from the reaction equation in question. We will illustrate. Discussion of use and application of Faraday's law given in the notes on pages 19 and 20. I hope you've looked at it. Talks about a battery running on the reduction of silver ion to silver, or maybe it's silver oxidized to silver ion, I don't remember. Doesn't matter, take a look. And the oxidation of zinc to zinc ion. 2 batteries. Question 18 then. First question, which is really presented to you as something to tackle. After considering the zinc battery, which is described on pages 19 and 20 in the notes, if you are assigned the task of constructing an electrically equivalent battery but made from aluminum rather than zinc, how much aluminum is required? The stipulations being that you want the aluminum battery to last as long as the zinc battery, and you want the aluminum battery to deliver the same current. So, all you're really asking to consider in this question is for the quantity of aluminum, for the quantity of zinc which is used to make the zinc battery, which is 2.50 grams. The zinc battery described is made out of 2.50 grams. What's the electrical equivalent of 2.50 grams zinc for the material aluminum? So, unit analysis. I'm looking at the question. What am I asked to determine? An equivalent quantity of aluminum. Now I can calculate this in moles or in mass. Well, let's go for moles, because we could always convert that to mass, grams of aluminum if we wish. So, I recognize, for starters, that as a mole of aluminum is oxidized, 3 moles of electrons are liberated. That makes sense? Do you know that the only positive oxidation state aluminum shows in its chemistry is +3? Which keeps with aluminum from family 3A losing 3 electrons per atom? Because aluminum in family 3A has got 3 valence electrons, a 3s pair and a single 3p electron. You did this stuff in 2045. So, in answering this question by dimensional analysis, the first factor I write down is 1 mole of aluminum per 3 moles of electrons. Because immediately in this first factor, from a unit standpoint, I have indicated the unit that I need to calculate, moles of aluminum. Now I want to see how this mole quantity of aluminum compares to electrically equivalent amount of zinc. Well, zinc on oxidation is 2 moles of electrons. So when I take and write 2 moles of electrons per mole of zinc and multiply that by my first factor, 1 mole of aluminum per 3 moles of electrons, moles of electrons goes away. Dimensional analysis. If I had this factor inverted, I'd have moles of electrons squared. That doesn't make any sense. All right? Now I have to recognize that the battery manufactured from zinc has been made using 2.5 grams of zinc. So somehow, some way, I've got to relate this mole quantity of aluminum that I'm trying to calculate to 2.5 grams of zinc. And you know, for any chemical substance, when you need a mole to mass or mass to mole relationship, what property of the substance gives you this information? Mole to mass or mass to mole relationship for a chemical substance?
Molar mass.
The formula mass, the molar mass. That's it. So from a factor or unit analysis standpoint, since in my second factor I got moles of zinc in the denominator, I'm going to take and invert the formula mass of zinc, write that in as my third factor so that now moles of zinc cancels from this setup I've created. And then when I multiply what I've got so far times the quantity of zinc from which the zinc battery was manufactured, I wind up with the unit that I have to get to answer this question properly, based ultimately on the quantity of zinc from which the zinc battery was made. That's it. And if you want to turn this into grams, and you get out the formula mass of aluminum, which is 27 grams per mole, and multiply 27 grams per mole times this. $22.19 says, let's imagine we have a metal chloride for which the general formula is MCl3. Do you see at a glance this tells us that the metal chloride in this material is in the +3 oxidation state? Because given that this is a metal chloride and chloride ions have a -1 oxidation state, the metal's got to be +3 oxidation state. That means if I want to make metal from this metal chloride, per mole of compound electrolyzed, I've got to pump in 3 moles of electricity to take the mole of the metal in the +3 oxidation state and convert it to 1 mole of elemental metal. And I think by now you've recognized that the Greek letter omega means what? Means electrolysis. Okay? So here's the chemistry that's going on. And what the question ultimately asks is, after having electrolyzed this 2.695 gram sample, after having electrolyzed the metal chloride to produce 2.695 grams of metal with a 10 amp current for 25 minutes, what's the metal? Well, if you're going to identify the metal by this kind of analysis, what property of the metal do you need to calculate?
Molar mass.
Formula mass, molar mass. So I'm thinking, how do I write a setup which unit-wise is going to give me the formula mass of the metal? Well, that's a ratio of grams for the metal per mole of the metal. So the first thing I'm going to write down is the mass of the metal that was produced by this electrolytic procedure. That's in the numerator. And along the line, as I continue to write this setup, in the denominator, I've got to refer to moles of metal. Then I've got to see to it that all the other units cancel. But I got to have it right if I do this. It's got to be right. That's the beauty of dimensional analysis. If you make a setup which gives you the unit or units that the statement of the question or problem demands that you get, you're right. It's nice. You can solve problems that are based on data, quantities with units that you've never seen before. Gazooks per squiggle, who cares? And if you think about dimensional analysis correctly, you can solve the problem. You won't understand what it is that you've calculated if you don't know what the units are. But you can still do the calculation properly because you've paid attention to and applied dimensional analysis. So as we said, for this we start with the quantity of metal produced at the cathode. And then I take advantage of this information because this tells me, as we've already stated, to produce a mole of metal from metal in this oxidation state, I got to pump in 3 moles of electricity. So my next factor is 3 moles of electricity per moles of metal. And look, I got mass of metal in grams per mole of metal. I've got the units I want. So what do I have to do? String together other factors, which are based on the current and the time for which the current was passed, and which will allow me also to eliminate this unit. Well, when I want to eliminate a quantity of electricity, or factor in a quantity of electricity, and I want this quantity of electricity to relate to time and or current, hey, we've already recognized a term that allows us to do that. It's called the Faraday. And dimensional analysis tells me that I need to eliminate unit-wise 3 moles of electricity. Moles of electricity. So I want the Faraday written like this, not moles of electricity over this, but this over moles of electricity. This system ran on a 10 amp current. The Faraday quantity put amperage in the numerator. So how do I get amps out of this setup? I divide by the current. If I multiplied by the current, I'd get amps squared. That wouldn't make any sense. Same with respect to time. I got to divide by the time. Otherwise, I'd get time squared. What does that mean? Nothing. And of course, this to convert between seconds and minutes. Do the arithmetic, as you've already done here, the part that matters. Look this molar mass up in the periodic table, you find out the stuff in question is chromium. Question 20 says, if instead I were to electrolyze magnesium chloride molten, where in this case I'd make magnesium at the cathode and liberate chlorine gas at the anode, for the same time with the same current, without doing any calculation, at least no calculation of consequence, certainly not applying Faraday's law, can I tell if this electrolysis process will give me more moles of magnesium or fewer moles of magnesium compared to moles of chromium contained in this quantity of chromium? By electrolyzing molten magnesium chloride at the same time with the same current, will I get more moles of magnesium or fewer moles of magnesium than moles of chromium which I produced by the chromium chloride electrolysis? Will I get more moles of magnesium or fewer moles of magnesium? Or will I get the same? I heard a vote for more. This damn bug I've been battling is still bothering me. So I won't do my usual ritual of inviting votes and such. Instead, I will ask, what property of magnesium do you have to pay attention to answer this question? Remember, the first electrolysis reduced chromium in the +3 oxidation state to elemental chromium. The second electrolysis is reducing magnesium in the only positive oxidation state that magnesium shows, which is +2 to elemental magnesium. So, if I'm running the same current for the same amount of time, am I going to be able to produce fewer moles or more moles of magnesium? What? You got to vote for fewer moles. Over there I had to vote for more moles. We have an argument amongst the ranks of our panel here. Now remember, when I multiply current times time, I get a quantity of charge. How much electricity have I shot through the system? If by electrolyzing the magnesium chloride, I wanted to make a mole of magnesium, then I would have to put in 3 moles of electricity. Okay? Now with the same current, running for the same time, if I wanted to make a mole of magnesium, if I wanted to make magnesium, if on electrolyzing the magnesium chloride, the chromium chloride, pardon me, this stuff, if I were to make a mole of chromium, how much electricity do I have to put in? 3 moles. So if I do the same thing to the molten magnesium chloride, I'm putting in 3 moles of electricity. How much magnesium am I going to make? 1.5 moles, aren't I? How about that? More moles of magnesium. Now then, if I weigh the magnesium, will I get a sample of magnesium that weighs more than this quantity of chromium or less than this quantity of chromium? If I weigh the magnesium, will I get a mass of magnesium that's more or less than, let's call it 2.7 grams? What property of magnesium do you have to pay attention to answer this question? Molar mass. What's the molar mass of magnesium? What is it? About, let's call it 24 grams per mole. Chromium is 52 grams per mole. Now I'm going to make 3/2 times the mole amount of magnesium, right? But the molar mass of chromium is more than double the molar mass of magnesium. So will I make a mass of magnesium which is greater or smaller than 2.7 grams? Smaller. Enough said. We go to the Nernst equation. Very important aspect of electrochemical arithmetic. An aspect or application of electrochemical arithmetic which is very often used to determine equilibrium constants. To my knowledge, equilibrium constants are most commonly determined by the Nernst equation. If you take a look at our table of half reactions in the notes, which is 45 half reactions long, you can calculate by application of the Nernst equation one hell of a bunch of equilibrium constants for any reaction developed from the half reactions in our table by coupling. You can get the K value for every one of those reactions. If you've read the information in the notes on Nernst equation, you'll see how application of the Nernst equation allows you to construct a pH meter. Look at table 2. Construction of a pH meter based on the information in Table 2 will likely involve, in fact it's practically a guarantee, one particular half reaction. Which half reaction do I refer? To which half reaction do I refer? I want to make a pH meter, and I want to make it using the half reactions available to me in Table 2. Which half reaction do you think is guaranteed to be part of this pH meter operating system? Give me the number of the half reaction. What's the number? 29. How does 29 read? Or better yet, never mind telling me how 29 reads. Tell me the electrochemical potential for 29. Zero. The standard hydrogen electrode. Remember where that comes from? Do you remember at the start of chapter 21? More aspects of thermodynamics? Because electrochemistry in the main is nothing but a particular area of thermodynamics. Start of chapter 21. We told you how we have to define a reference point to get thermodynamic information for ions in solution. The solutions don't exist at absolute zero. So the third law of thermodynamics is worthless when you're talking about doing solution chemistry. And what was the reference point we defined? Forming a solution of pH 0 has a delta G 0 value of 0. And since delta G 0 equals minus NFE 0, where N is moles of electricity and F is the Faraday, if delta G 0 is 0, then E 0 is 0. And that's the standard hydrogen electrode. Number 29 in the table. This 29 in the table shows you forming the hydronium ion from its component materials under standard state conditions. So, for that half reaction, E0 is 0. If nothing else, if I make my pH meter using this half reaction, I've simplified the arithmetic, because any values that I actually have to deal with have got to come from the other half reaction, not from the standard hydrogen electrode half reaction. The Nernst equation is derived in the notes. It all comes from delta G equals minus NFE and delta G 0 equals minus NFE 0. But as usual, I'm not interested in holding you responsible for the derivation. Likely you've noticed that on the information sheet the Nernst equation is offered, just like the Faraday's law equation. Here's the Nernst equation in its most familiar form. 0.059 term comes from a combination of constants, which involve R, the ideal gas constant, T, taken as 298 K, because E0 is proportional to delta G0, so I've got to specify temperature, since delta G0 depends on temperature. All of this times the log of Q, and in this case Q is not charge. In this case, Q is the reaction quotient. You remember that the reaction quotient has the same chemical form as the equilibrium constant. What's the difference? In Q, we can deal with any possible set of values for the system. Concentration values, if the system involves solution components. Partial pressures if the system involves gas phase components. But if we're under equilibrium conditions, then all the terms in Q are equilibrium values. And if we're under equilibrium conditions, therefore Q is equal to K. And if we're under equilibrium conditions, if I'm going to use the Nernst equation to calculate an equilibrium constant where Q is equal to K, what's the value for E cell? 0. We're at equilibrium. Delta G is 0. E for the system. Not E0, but E for the system is 0. So let's do some applications of Nernst to this electrochemical system. Recall, if you will, in our last conversation, we talked about zinc reducing hydrated copper ion, where zinc got oxidized to hydrated zinc ion, and hydrated copper ion got reduced to copper metal. That system is here expressed in what's called standard cell notation. I mention this now because I didn't have time to mention it last time. Standard practice to write an electrochemical cell in standard cell notation like this is to start with the anode material itself, zinc metal for this particular system. Then write the formula for which the anode, or what the anode is oxidized into. In this case, zinc is oxidized into this stuff. With zinc being separated from hydrated zinc ion by this single vertical line. Single vertical line in standard cell notation is simply a phase separator. Because this is solid and this is aqueous phase, liquid. Then with a double vertical line, we separate the half cell in which oxidation occurs, the anode half cell, from the half cell in which reduction occurs, the cathode half cell. What does the double vertical line symbolize? Besides separating the anode half cell from the cathode half cell. Salt bridge. The double vertical line is a symbolic representation of whatever device is used to interconnect these two systems, because we have to keep in mind, for an electrochemical cell to function properly, to give us usable electrical energy, we have to force the electricity that travels from the stuff being oxidized to the stuff being reduced. That flow of electrons has to flow through an external circuit. You cannot operate an electrochemical cell if you have the material that's being oxidized in immediate contact with the material that's being reduced. Now, if you do that, electrons still flow, but they won't be flowing through your external circuit. They will not be electrons which you can harness and use. That's a short circuit. We don't want that. And so, on the immediate right side of this half cell separator, we have the formula for the stuff that's being reduced, the oxidizer, and then another vertical line, in this case, since this is aqueous phase, because this is reduced to copper metal, solid phase, which is our cathode material, if we reduce this on the surface of copper. Now, we'll finish by you taking a look at the half reactions. Do that right now. Look at table 2. Tell me. If we have this electrochemical system, zinc bar connected by an external wire to a copper bar. Zinc bar sticking in, say, 1 molar zinc sulfate solution, where I have hydrated zinc ions. Copper bar sticking in, say, 1 molar copper sulfate solution, just like we did demonstration-wise, where I have hydrated copper ions. With the 2 half cells interconnected by our salt bridge. If I give you 6 molar ammonia, can you treat this electrochemical system in some fashion so as to make E cell and E zero cell go up relative to E cell and E zero cell for this system? Now look at what you can do with the ammonia. You can say, no, the system operating most optimally this way, so I don't add ammonia to either half cell. Or you can add ammonia to both half cells. Or you can add ammonia to this half cell only. Or you can add ammonia to this half cell only. You got 4 choices. What's your choice? What is the correct choice? Look at the table of half reaction. What are you going to do with the 6 molar ammonia to increase the operating potential for this electrochemical system? By treating the system as you so choose with 6 molar ammonia. What does the table of half reaction information tell you? The table of half reaction information is in fact a table of thermodynamic stabilities. Do you see a half reaction in the table which shows oxidation of zinc to the zinc ammonia complex ion? Do you see a table, a half reaction in the table where you see copper being oxidized to copper ammonia complex ion? You see both of those. And you see in each case that the ammonia complex of the metal ion is more stable than the water complex, don't you? Okay. So what do you do with the ammonia solution? Put it in both half cells? You put it in the anode half cell only? The cathode half cell only? What do you do with it? You put the ammonia solution in the anode half cell only. Now one more statement. Since we're running a little bit behind with this stuff, I'm going to take a look at one more video. Post a reminder regarding this video on Sakai, so that sometime this weekend you can take a look at one more video to get additional information on electrochemistry. Look at Sakai, effective tomorrow. Got it.
Notes in a pile up here.